Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 22 on the NPTEL course on fluid mechanics for undergraduate chemical engineering students. The topic of our discussion today is differential balance of linear momentum. In the last couple of lectures, we have started discussing differential balances, and first we derived the differential balance of mass, and that went by the name of that goes by the name of continuity equation. Okay. The key thing about differential balances is that they are valid at each and every point in the fluid, and the form of the form they take are by way of differential equations. That is why they are called differential balances. And today we are going to focus on the differential balance of momentum. Specifically, we are going to look at linear momentum. The starting point for this deriving the differential balance is essentially you take the integral balance that we derived for Cv for a control volume, and we are going to apply it to a control volume that is of infinitesimal size, that is in the limit as the control volume shrinks to a point. So, recall that the differential balance the integral balance for momentum for a control volume is sum of forces acting on the control volume is equal to the rate of change of momentum present inside the control volume plus the momentum flux that goes in and out of the control volume by virtue of fluid flow. Okay. Now, we are going to apply this to an infinitesimal cubic control volume, just as before we are done for mass. Okay. So, x say x, y and z. So, this is delta x, delta y and delta z. So, these are the three sides of the control volume, and we are going to take the limit as this control volume shrinks to a point. Now, as I have mentioned before for mass conservation, the chief simplification that arises out of an infinitesimal control volume is that this integrals can be simplified in the following manner. Now, in the limit as the control volume shrinks to a point, the control volume itself becomes so small that this quantity rho v can be taken outside the control volume, okay, outside the integral, because it is the control volume is so small, the domain of integration, volume integration is so tiny that you can pull the integral outside the integrand outside the integral. So, that is our approximation that we do. So, d dt of rho v times delta v, where delta v is the volume of the control infinitesimal control volume, is equal to delta x times delta y times delta z. Okay. So, that is the first term. The second term simplifies because of the fact that here, since the control volume is so tiny, you can assume uniform flow approximation, that is the velocities v rho times v dot n can be pulled out of the area integral, because they vary so little across the cross section. Okay. Now, we also know that v dot n is v plus v for outlets and v dot n is minus v for inlets. Okay. Outlets minus v for inlets. Using this, we can write this equation as summation of all the external forces acting on the control volume is equal to d dt of rho v times delta v plus summation over all outlets times rho v a times v dot n sorry rho V A times V plus summation over all inlets rho V A, okay, times V, where I is the index that goes over various outlets. So, there is a minus sign because you know that V dot n is minus for an inlet. Now, rho V A is nothing but the mass flow rate. So, I can simplify this further as times delta V plus summation over all outlets times m dot I times V I minus summation over all inlets times m dot I times V I, where the index goes over various outlets and inlets. Now, if you look at the control volume is a tiny cube, okay, have x, y and z. So, you have faces at x equal to 0, faces at this is at x equal to 0, okay. This is the face at x equal to x plus delta x, okay. So, we can call it any x, okay. So, just to be general. So, there are two faces, one is the left face, the face at x, the other is the right face, the face at x plus delta x. So, in general momentum in the x direction, along the x direction, momentum can come in through the face at x and go out through the face at x plus delta x, or it may do otherwise also, but just for the sake of clarity we will assume that momentum is coming in like this and momentum is going out like that. And similarly, momentum can come in at through the face at y and go out through the face at delta y, okay, y plus delta y, and likewise momentum can come in through the face at z and go out through the face at delta z. So, there are various contributions to the in and out terms of the momentum flux, okay. So, we will further write this as, so the momentum flux at face x, the momentum enters at face x. So, the momentum flux is simply rho u times v. So, I am writing this term, okay, this term, this is m dot I times v I, okay, rho u times v times dy dz, okay, and at the outlet all evaluated at x, okay, the outlet is at face x plus delta x. So, you will have rho u times v dy dz at x plus delta x, okay. Remember that we are going to use Taylor expansion for this term. So, rho u v at x plus delta x is rho u v at x plus d dx of rho u v times dx, but you have to multiply the entire thing by dy dz. So, we will add dy by dz, dy dz, that is the cross sectional area through which momentum is flowing. So, dy dz dx dy dz, okay. So, similarly you will have the face at y, momentum in the y component of the momentum enters, okay, sorry, the momentum enters that the momentum that enters through face y is simply rho v times v times dx dz evaluated at y, okay, and momentum out at y plus delta y is rho v v dx dz evaluated at y plus delta y, which is nothing but rho v v plus d dy of rho v v times dy times dx dz. let us say area. Similarly, the phase Z, momentum enters, that enters is rho w v dx dy, and the momentum that leaves is rho w v dx dy at z plus delta z. Okay. So, having done all this, we can substitute all these terms into the balance. Okay. The sum of all forces acting on the CV is equal to d dt of rho v times delta v plus rho u v times dy dz. This is the momentum that exits at phase x plus delta x, plus d dx of rho u v dx dy dz minus the momentum entry at x is simply dy dz. Okay, these two terms are going to cancel out. Okay. Similarly, there are other two phases, plus rho v v dx dz plus d dy of rho v v dy dx dz minus rho v v dx dz. These two terms are going to cancel out. Okay. And then the final, the plus the through the momentum that enters and exits through the z phase is simply rho w v dx dy plus d dz of rho w v dz dx dy minus rho w v dx dy. So, these two terms will cancel, leaving us with the following simplified equation: sum of all the forces acting on the control volume is d dt of rho v times delta v plus d dx of rho u v times delta v. So, I can take delta v common, plus d dy of rho v v plus d dz of rho w v. Okay. So, I can pull delta v entirely from the and I can take it common. So, that will give us, this is sum of all forces is equal to delta v times d dt of rho v, plus this can be written as del dot rho v v. Okay. So, that is the del dot rho v v. This can be simplified further as follows: rho v plus v dot del rho v plus rho okay. So, let me simplify the entire thing. We can write this as rho dv dt plus v d rho dt plus v times del dot rho v plus rho v dot del v. Okay. Now, these two things are essentially, this is essentially v times d rho dt plus del dot rho v, that is identically 0 by continuity equation, conservation of mass. The differential balance of mass has already given us the same equation by continuity equation, by mass conservation. So, we are left with the following term: summation of all forces that act on the CV, external forces that act on the CV, is del V times rho dV dt plus V dot del V. This is nothing but del V times rho times the substantial derivative of velocity. Okay. So, this is the local acceleration, as we have seen several times. This is the convective acceleration. Okay. This is the local acceleration, this is the convective acceleration. Combined together you get the substantial derivative, that is the total acceleration of fluid particle. Now, rho is mass per unit volume times the tiny volume is the mass. So, mass times acceleration is equal to sum of forces. This is essentially Newton's second law, but applied to a very tiny piece of fluid that is present in the CV. Now, we have to worry about this term. What are the forces that act? What are the forces that are acting on the surfaces of on the CV? Okay. These are the external forces that act on. So, to remind you, our CV is simply a tiny cubic volume element, an infinitesimal cubic volume element. Okay. So, this is our CV, okay, with volume delta V equals delta x times delta y times delta z. Okay. So, what are the forces acting on the CV? In general, one distinguishes two types of forces on the CV. The forces that act through the entire volume of the CV are called body forces, and one common example is gravitational force that acts on the entire volume of the fluid. The forces that act only on the surface of the CV, that are exerted by the neighboring fluid elements, they are called surface forces. And pressure is one example of a surface force. It acts only on the surface. Okay. First, so we can worry about the body force very easily. The body force that acts on this tiny control volume is nothing but rho times g times delta V. This rho g times delta x times delta y times delta z. This is rho times delta V is the mass per unit volume times acceleration due to gravity is the gravitational force acting on this control volume. Okay, so that is simple. Now, we have to focus on surface forces. That is slightly more involved. So, we will go through this a little slowly. Okay. So, surface forces. Okay. Now, if you look at this cubic element, let us draw the cube again. Okay. The cube has 6 faces, x, y, z. Now, each face is denoted by, so this is the face whose unit outward normal. So, each face is now characterized by an unit outward normal. For this face, the outward normal is simply in the plus I direction, whereas for this face the unit outward normal is in the minus I direction. For this face the unit outward normal is in the j direction, okay, and for this face unit outward normal is in the k direction, and so on. So, there are 6 faces, and therefore, there are 6 unit normals that represent the orientation of these 6 faces. Now, at any face, the force exerted by the fluid on the neighboring side of the control volume on this face can be in any direction. This is the surface force. Okay. So, let us call that surface force as delta F. We are calling everything as delta because small, because we are worrying about a tiny control surface. Okay. So, in general, okay, this force that acts on a surface. So, this is the force that acts on a surface whose unit normal is in a particular orientation. For example, in this particular case, this is I. This will have two contributions. So, let us now draw a generic surface which has a unit normal, okay, and this force can in general act in a particular way, delta f n. This will have a component in the direction of the unit normal, that is called the normal component to the force, okay, delta f n, okay, and there will be a component in the plane, okay, and there will be two for any surface there will be two tangential components. So, this n is equal to I in this particular example. So, the two tangential components will be in the direction of j and k. Okay. So, the force acting on any given plane, any given surface can be resolved into the three components along the three coordinate directions. One along the normal to the along the direction of the normal to the outward normal to the surface, the other along the direction parallel to the direction of the along the two directions parallel to the direction of the surface. So, accordingly these two forces are called the normal stress. Stress is force divided by unit area on which the force is acting. So, the normal stress is sigma denoted by sigma n. Sigma n is limit delta A tending to 0, okay, delta f n divided by delta A n. Let delta A n be the area of the surface on which the force is acting, and in the limit as this area shrinks to a point, then you will have a force per unit area acting at each and every point in the fluid. Similarly, the shear stress, okay, is denoted by tau, okay, tau n. Okay, n stands for the unit normal, the subscript n stands for the unit normal of the orientation of the surface on which the force is acting. Okay, tau n is limit delta A tending to 0, delta f tangential, okay, which is in the action in the direction of the in the direction parallel to the surface divided by delta A. Okay, I will give you, this is the general definition. Okay, we can of course resolve it in many concrete ways as follows. Okay, for this particular surface, at you are now considering a surface whose unit normal is in the plus I direction. Okay, this force can be resolved into a normal component which is delta f x, a component along y delta f y, and a component along z delta f z. Okay, so correspondingly you can define stresses like follows: sigma x x is limit delta A x tending to 0, okay, in the limit as the area shrinks to a point, you divide the force acting on the surface in the normal direction x direction divided by the area. Okay. Now, you can also define tangential or shear stresses. This is the normal stress, okay. These are shearing or tangential stresses, shear stress. Okay. Now, this can be written as tau. Now, there are two components to tangential stress. One is in the direction of y. So, limit delta A x tending to 0, the y component of the force divided by the area delta A x. So, likewise you can have tau x z, this limit delta A x tending to 0, delta f z by delta A x. So, notice that there are two subscripts to the stresses. The first subscript in our convention x denotes the plane on which the force is acting. Here it is in the direction of the unit normal I. So, it is the direction of the unit normal outward normal to the surface on which the force is acting. So, the unit outward normal on this surface is in the x direction. So, this x points to that. The next direction, sorry, the next subscript denotes the component of the force. So, sigma x x is the force per unit area acting on a surface whose unit normal is in the x direction and the force is in the x direction. Tau x y is the force in the y direction acting on a surface whose unit normal is in the x direction. Tau x z is the force that acts in the z direction on a surface whose unit normal is in the x direction plus x direction. Okay. So, there are two subscripts associated with the stresses. Okay. So, if you notice, a vector like velocity can be written as V x times I plus V y times j plus V z times k, the components along the 3 coordinate directions times the unit vectors. So, there is only one subscript x, y and z, because there is only one direction associated with velocity, namely the direction of the velocity. But if you consider a concept like stress, there are two directions associated with it. One is the direction of the force. Stress is force divided by unit area. So, force itself is a vector, so it has a direction associated with it, and so does the area, because any area has an unit outward normal. So, the orientation of the area provides you another direction. So, there are two directions associated with a quantity such as stress. So, these are called tensors. So, the stress in a fluid is a tensor because it has two directions associated with it. One is the direction of the force that is acting on a given surface, and the other is the direction of the unit outward normal to the surface. So, these are the two directions. So, the vectors like velocity have only one physical direction associated with it, namely the direction of motion is the direction of the velocity. Okay, but quantities like stress has quantities such as stress have two directions associated with them. So, they are called tensors. Specifically, they are second order tensors because there are only two directions. There are also higher order tensors which can have more directions associated with them. Okay. So, now just as we defined stresses on a plane whose unit normal is in the plus x direction, we can also consider a plane whose unit normal is in the plus y direction. So, we will get tau y x is limit delta a y tending to 0 delta f x by delta a y. Tau y y is limit delta a y tending to 0 delta f y by delta a y. So, this is sigma because it is a normal stress. So, it is denoted as sigma. Tau y z is limit delta a y tending to 0 delta f z by delta a y. Okay. Now, here again the two subscripts have the following meaning. The first subscript denotes the direction of the unit outward normal. So, the unit outward normal to the surface is in the plus y direction. That is why this first subscript denotes the direction of the unit outward normal to the plane, to the surface over which forces are acting. On which forces are acting by the neighboring fluid, by the adjacent fluid. The second subscript tells you the direction of the force, because the force acting on a surface with a given unit normal itself need not be exactly in the direction of the unit normal or the direction perpendicular to the unit normal. It can in general act in any direction. Therefore, you need to resolve that force into 3 components. So, you have these 3 components, and you also have the force acting on the z plane. Okay. So, tau x tau z x is limit delta a z, tau z y is limit a y tending to 0 tau z z. So, it is a normal stress. So, we denote normal stresses by the Greek letter sigma is limit delta a z tending to 0. Okay. So, again z is the direction of the unit outward normal to the test surface over which forces are acting, and the second subscript x y z denotes the direction of the force on which the force on the surface, direction of the force which is acting on a given test surface. So, as the control volume over which we are writing this balance, okay, we are taking a cube centered about a point with infinitesimal sides. As this control volume shrinks to a point, the state of stress in a fluid is denoted by this set of 9 components. So, you have sigma x x, tau x y, tau x z, tau y x, sigma y y, tau y z, okay, tau z x, tau z y, sigma z z. So, this looks like a 3 by 3 matrix. These are, so the components of the stress tensor are written in the matrix form. Components of the stress tensor. Suppose you may ask, what is the use of knowing the stress tensor? If I have a coordinate system, if I consider any point in the fluid, okay, I can construct a surface on this point with any arbitrary orientation, and there are infinitely such many orientations about a point. You can keep a tiny plane and you can orientate any way you want, and there are infinite number of orientations. So, what is the state of stress on any arbitrary orientation n? So far we have just discussed about the direction, the stresses acting on planes or surfaces which have well defined unit normals, that is either they are in the plus x direction I, plus y direction j, or plus z direction k. But nothing forces us to have only orientations which are aligned along the coordinate directions. In general, you can have any arbitrary orientation n x n, which is denoted by the unit vector n, which is n x I times n y j plus n z times k. Okay. Now, if you have such a tiny area element with arbitrary orientation, what is the stress, the force per unit area acting on that such a surface? Okay. Let us call that sigma x, sigma y, sigma z acting on that surface. This is called the Cauchy's stress relation, which will not prove. It turns out that one can show that you can relate the stress on an arbitrary plane with an arbitrary orientation at a given point to the components of the stress tensor, which tell you about the forces that act on well defined coordinate directions through a simple matrix multiplication. You take the stress tensor, write down the components as a 3 by 3 matrix, do a matrix multiplication with the 3 components of the unit vector. So, if you tell me what is the orientation of the vector, and if you also tell me what is the state of the stress in the system by telling the components of the stress tensor referred with respect to a Cartesian coordinate system, then I can tell you what is the stress at any arbitrary orientation. Now, this is a very powerful result, because in principle you might have imagined that to find the stress at a point, and since you have to specify also the orientation of the surface, you have infinitely many orientations. You may imagine that you may have to tell a whole lot of information, because you have to keep on changing the orientation to find what is the stress. But the Cauchy relation tells us that it is not necessary to keep on measuring or calculating at infinitely large number of orientations. All you have to do is to measure the force per unit area at along the 3 coordinate directions, and once you have it, you can find what is the force that acts per unit area on a surface with any arbitrary orientation about that point. Okay. This is the power of the Cauchy stress principle. Okay. Now, whenever we define things like stress or work, there is always a sign convention. So, we have to be a little clear about the sign convention. Okay. If I say that tau y x is positive, is let us say is equal to 10 Newton per meter square, for example, what does this mean? Okay. First of all, we have to understand the two subscripts y and x. Y is the direction of the unit normal. So, you are essentially thinking of a surface whose unit normal is in the plus j direction, okay, and x is the direction of the force. Okay. So, we are now saying that on a surface whose unit normal is in the plus j direction, there is a force which acts per unit area of the surface with a magnitude of 10. Okay. Now, it also turns out that if I say tau y x is 10 Newton per meter squared, now at the same point you can also construct a surface whose unit normal is in the minus j direction and the force is acting in the negative x direction. So, this is x, y and z. Okay. So, if I say tau y x is 10 Newton per meter squared, it either means that a force of plus 10 Newton per meter squared is acting on a surface whose unit normal is in the plus y direction, or it also means that a force of magnitude 10 Newton per meter squared is acting in the minus x direction on a surface whose unit normal is in the minus j direction. Okay. But you can see that this is actually a consequence of Newton's third law, because if you take the same point, okay, the sum of forces acting on this surface is equal and opposite. Okay. Therefore, this is essentially a consequence of Newton's third law of motion. So, if instead a force, if I say tau y x is minus 10 Newton per meter squared, then what it means is that according to the sign convention, so y means the first subscript is, so let us draw this slightly below. The first subscript y means that you are considering a unit normal in either, I mean let us say it is in the plus y direction, then the magnitude of the force is in the minus x direction. So, this is x, this is y. So, the force is acting in the minus x direction. Instead, you could also choose at the same point the direction of unit normal to be in the minus y direction, then the force will be acting in the plus x direction. This is because of Newton's third law, because if you consider a given point and you consider a surface about that point, okay, there are equal and opposite forces acting on that surface. So, this sign convention tells you basically the following: if I say that a force, the magnitude of the value of the force is positive, then either a positive direction of the force is acting on a surface whose unit normal is in the positive direction. So, where the first subscript tells you the direction of unit normal and the second subscript tells you the direction of the force. So, if I tell you tau y x is plus 10 Newtons per meter squared, that means that you can say that if I construct a unit normal to the surface in the plus y direction, then the force is acting in the plus x direction, or if you construct a unit normal is in the minus y direction, the force is in the minus x direction. So, the direction of the force and the direction of the unit normal, either they are both positive or negative, if I tell you the value of the force to be positive. If I tell you the value of the stress component tau y x to be positive. If I say that it is negative, then if you construct the unit normal to be in the plus direction, y direction, the force is in the minus x direction. Vice versa, if you construct the force unit normal is in the minus y direction, then the force is in the plus x direction. So, if the value of the stress component is negative, then the direction of the force and the unit normal are either one is positive, the other is negative, and vice versa. So, that is the sign convention that is followed in our course and most of the textbooks. Okay. So, essentially what we are now saying is that if you tell me the if I take a point, arbitrary point, and with an arbitrary unit normal n with components n x, n y, n z, then what we are saying is that if you have a surface, if you have a tiny area A, then the force acting in the x, y and z direction per unit area delta A is delta is the magnitude of the area, is nothing but the value of the stress components that are acting on the 3 Cartesian directions times the unit components of the unit normal to that arbitrary plane. Okay. That is the simple meaning of our stress tensor. Okay. Now, normally what is done is that the normal suppose you look at a static fluid, then the forces act purely normally to any surface. So, for a static fluid, sigma x x is minus p, sigma y y is minus p, sigma z z is minus p, because the pressure acts to compress. So, pressure acts, as we have been telling several times, the pressure acts in the direction of minus n. So, you have minus p. So, in a static fluid, the state of stress is given by simply minus p 0 0 0 minus p 0 0 0 minus p. Okay. In a flowing fluid under motion, it is normally a usual convention to write the total normal stress as something that is existent even in a static fluid plus the normal viscous stress. This is called the normal component of the viscous stress or the shear stress. It is more appropriate to call them as viscous stresses because they are acting in the purely normal direction. So, sigma y y is minus p plus tau y y, sigma z z is minus p plus tau z z. Okay. So, therefore, we have this split as to what the normal stresses are. They are comprised of the pressure force which is already there in a static fluid, and then plus the normal component to the viscous forces. Okay. So, now recall that the momentum balance that we wrote was summation of all forces is rho delta v times dv dt. Okay. Now, this force has two components, the body force which is rho delta v times g plus the surface force, and it is in the quest of what the surface forces are that we went into the notion of the stress tensor in detail. Okay. So, now we have to write down the net surface force in the x direction, y direction and z direction. Okay. So, let us call this, since it is an elemental area, we call it d surface. It is a vector. So, we have to now worry about the surface forces in the various coordinate directions. Okay. dfs is the surface force. So, this has components dfs x, dfs y, dfs z, the three along the 3 directions, coordinate directions. So, what is dfs x? Is nothing but, so what we are saying is that now we are considering the force in the x direction. So, you are considering the CV. So, we have to be a little more careful about this. You are considering the CV. Okay. Okay. And if you know, this is x, y, z, this is the, if you recall, this is what we did. Now, we are going to consider all the forces in the x direction acting on the CV. The force acting on this plane is sigma x x. The force acting on this plane in the x direction is tau y x, and the force acting on the plane whose unit normal. So, this side plane is tau z x, because the unit normal is in the plus z direction and the force is acting in the plus x direction and so on. Okay. So, this and similarly forces are acting also in the other 3 directions, which we will write down. So, the total force in the x direction is nothing but you have sigma x x, that is acting here, this is at x plus delta x, times dy dz times the area of the surface over which this force is acting. Now, you have to add all the forces, but this force is acting, the unit normal to this is in the minus x direction. So, you will have a negative sign for this. Okay. Sigma. So, in principle you have to add forces, but since the unit outward normal is in this direction, the force will also be in the negative direction. Okay. So, plus tau y x at x plus delta x dy dz, sorry, now we have to be a little careful, times dx dz, this is the area over which things are acting, minus tau y x at x dx dz plus tau z x, okay, this is at, sorry, this is at y plus delta y, this is at y, minus tau z x at z times, so this is dx dy now we have to use the Taylor series expansion. Okay. We have to use the Taylor's expansion. Again, to reiterate, this negative sign we have to simply add all the forces in the x direction. So, but this negative sign is because of the fact that this unit normal is acting in the minus x direction. Similarly, this unit normal on this face is in the minus y direction, and this unit normal on that face in the minus z direction. After doing Taylor's expansion, you will find that df s x is sigma x x plus d sigma x x dx times dx times dy dz minus sigma x x dy dz plus tau y x plus d tau y x dy dy dx dz minus tau y x dx dz evaluated at x. Okay. After doing Taylor expansion, plus tau z x plus this is all evaluated at x, I mean this is at y and so on. D tau z x by dz times dz evaluated at z dx dy minus tau z x evaluated at z dx dy. You can anticipate the cancellation of several terms as follows. Okay. So, this term will cancel this term will cancel this term will cancel this term, leaving us with essentially df s x is d sigma x x by dx plus d tau y x by dy plus d tau z x by dz times dx dy dz. So, and likewise df s y is d tau y x by dx plus d sigma y y by dy d tau x y by dx plus d tau z y by dz times dx dy dz dfz s is, okay. Likewise, you can write this as d tau xz by dx plus d tau yz by dy plus d tau d sigma, because the normal stress, dy dz. Okay. So, we had this momentum balance to be rho dV by dt is rho g delta V plus the surface force acting on this differential control volume. Okay. This will become, if I now write various components for the sake of clarity, rho du dt is rho g x, the x component of the gravity, plus delta f s x, but that is nothing but rho g x delta V, plus we just derived this as delta f x, if you recall, is this entire thing. Okay. So, we have to simply use that, plus delta V times d sigma x x dx plus d tau y x dy plus d tau z x dz, so times delta V. So, you can see that this is the x component of the momentum balance, differential momentum balance. You can see that this delta V will cancel out uniformly throughout the equation, leaving us with the simple equation rho du dt is rho gx plus, for sigma x I am going to substitute as minus p plus tau xx, okay, plus d tau xx by dx plus d tau yx by dy plus d tau zx by dz minus dp dx. Likewise, I can do the y and z component of the momentum balance. I will not do the algebra separately, but you can easily see that you can do it by just analogy. Now, I am splitting the normal stress into pressure plus normal viscous stress. Okay. Then the z component of the differential momentum balance okay. So, this completes the derivation of the differential momentum balance. These are called the Cauchy stress balances or the Cauchy momentum equations. The interpretation of this is very simple. Okay. I can also write it in vector form, rho dV dt is minus del p plus rho g plus divergence of the stress tensor. Okay. So, just as you had a divergence of a vector which gave you a scalar quantity, divergence of a second order tensor will give you a vector. Okay. So, this is mass times acceleration acting per unit volume of the fluid, okay, that is equal to sum of all forces. What are the various forces acting? There are pressure forces acting per unit volume, this is the gravity forces acting per unit volume, and these are the viscous stresses acting per unit volume. This is the rate of change of momentum, mass times acceleration, okay, per unit volume. Acceleration per unit volume of the fluid. So, the final interpretation is very simple and it is very analogous to Newton's second law of motion, but also although the form of the equation is slightly more complicated, and remember that the substantial derivative disguises a more complex term, it is dV dt plus V dot del V. Okay. So, this is the Cauchy momentum balance. We will stop at this point and then we will continue from here in the next lecture, okay, and we will develop what are called the Navier-Stokes equation for a Newtonian fluid.